Hi there. Well, I think I lied to you in the last video. I said we were going to move on and evaluate limits analytically or algebraically, and we're going to get to that, but we first need to talk about when limits don't exist, and this is the second time I've actually made this video. The first time I did it, the sound was turned off on my microphone, so really excited about that. Anyway, let's go ahead and get started here. When limits don't exist, okay, we saw from our definition of a limit the other day, we said that this limit, as x approaches c of some function, we said that that equaled L, and that this notation right here implied that x is approaching c from both directions, and that's going to equal L if f approaches that L, that same L, as x approaches c from both sides of it. Okay, so when can we write does not exist over here instead of some number or some limit? Well, turns out there's three times when that actually happens, and the first time this happens is when the right and the left-handed limits, when they disagree. Okay, for instance, let's say we have some function, and maybe we have this line, this linear function. Maybe there's a closed dot here, and then down here we have maybe an open circle, and maybe it does something crazy like this. Okay, passes the vertical line test, I think. So we know this is a function. So you could probably bet that we're interested in our limit right here. If this was our c, what would be the limit of that function as x approached c? Well, just using the graph here, you can see that as we approach c from the right-hand side, okay, as x gets close to c from this direction, that your function value is approaching whatever this y value is right here. Well, let's just call it L. Okay, so the right-handed limit, which we could actually write the limit as x approaches c, the little plus above it, and this, oops, that's a plus. There we go, sorry. I know that's sloppy. So this is the limit as x approaches c from the right-hand side. That's what that notation means. Of f of x equals, in this case, it equals L. Okay, now, if we jump back over here and we let x approach c from the left-hand side, you can see that your function is kind of zeroing in on this y value down here, which is not L. Maybe it's some other number. It looks negative in this case, but we'll just call it M. Okay, in other words, the limit as x approaches c, in this case, from the negative direction. Okay, that just means approaches c from the left, of f of x is equal to M. Now this M and this L are different. Okay, those guys are different. And because they're different, we can say that the limit as x goes to c, now again, remember this is implying that x is approaching c from both directions. Okay, well, we can't state L and M. That wouldn't be right. They're two different numbers. So there is no limit here. So we could say does not exist. That's an E. Apologize for my penmanship here. That's horrible. But hopefully you get the idea that if the left and right-handed limits disagree, we cannot make a definitive statement that this thing is bounded by any one number as you approach that C. Okay, the second case that a limit doesn't exist is when f of x is unbounded as x approaches some c. Okay, so let's make a c value right there, and maybe at this c value we have this asymptote. That's supposed to be a dashed line. Okay, that's an asymptote of some sort. And maybe we have this function that as we get close to that asymptote, it blows up to positive infinity. Okay, so you can see, hopefully you can see, that as we get close to c from the right, okay, that your function is not zeroing in on any particular number. It's actually getting bigger and bigger and bigger the closer we get to c. Turns out it does that from the left as well. So you get close to c from this direction, your function value simply goes to positive infinity. Okay, so we can write the following. We can write the limit of f of x as x goes to c equals, now there's two ways you can do this. I can go ahead and write does not exist, kind of like I did up here, and that would certainly be correct on any quiz or test that you might take. You would be correct in stating that, but you might find some people in some books write positive infinity, and I don't want you to be confused about this. Infinity, first of all, is not a number. It's a concept. A lot of people like to think of infinity as a number, and it's not. And really, by writing positive infinity here, you really are stating that the limit doesn't exist. You're simply stating how it doesn't exist. So this right here is actually a little bit more specific than this. If I just wrote does not exist, then that would certainly get the point across, but stating that it's positive infinity gives us some idea how this function doesn't, how the limit doesn't exist. So I hope that makes sense. The third and final time that a limit of a function doesn't exist as you approach a particular value of c is what I call this oscillating behavior. Oops, sorry. I was just switching colors there. So let's say we have this value of c right here, and maybe this function is kind of coming in here, and maybe here it goes up and then it comes back down, but the closer we get to c, these little movements get tighter and closer together, and then the further away from c we get, maybe they spread out a little bit more. Okay, that's not a very good picture, but the idea is that the closer we get to c on both directions, this function is just bouncing up and down, and it's not really coming down on any particular value. Okay, so in this case as well, we could go ahead and state that the limit of f of x as x approaches c, we could go ahead and state that it does not exist. Okay, and graphically this is the hardest one to kind of imagine, especially with a horrible picture like that. I apologize for that. Graphically, I think these two up here are a little bit easier to see why those limits don't exist. But when we get into some examples in the next video, this will become pretty clear why it doesn't exist. So in the next video, we'll go over some more specific examples on the calculator of when limits can fail. We'll see you then.